Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon to all. Now we look into the second part of the neural network usage for control. We call it part 2B, and basically we're talking again a bit about inverse modeling and the control strategy methods that we are going to use using neural network models that we have obtained before from the modeling side or identification side, we call it. Okay, basically a little bit repeat of what we talked last week. Last week we had the last lecture, last part, part 2A, the dynamic state modeling, which is made up of the feed-forward modeling, which is a normal modeling process where we put input, we get output. But we can also have what we call inverse modeling, inverse of the model basically, when we put in the output to get the input. Just the inverse. The normal modeling process to get inverse may be complicated due to the new nonlinear structure. The neural network is much easier to get. It's just a matter of switching the input-output data. So what it defines is basically predicting the present manipulated input, which is the U, with presentation of the past and present system input and output together with the required output. For control, it's called a set point. If it's used for modeling, then we can say it's a required output. When we're talking about control, it's the set point. We put the set point, we want to know what we are going to get for the input. That's basically the inverse model. The perfect inverse model is the controller itself. What we want is the set point. What is the controller input or manipulated input that we need to get out to the process to give us a set point. So definitely it's a perfect controller. If you have a perfect inverse model, it's a perfect controller. If not, you'll have to put some extra touch up or some extra addition point values to make up for the non-perfect inverse model. So we have two configurations we can get in terms of the neural network structure. What we call the general method, the specialized method to get the inverse model, and then this can be used. These inverse models can be used as controllers in different strategies, because they are the inverse model is the control itself, so that you can put into different strategies and call it different names. But to get inverse modeling, we have two methods basically. As I said just now, is the general method, which is called open loop, or the specialized method called the closed loop. This is a generalized method. This is basically the inverse of that forward modeling process that we taught to you the last lecture. We put the use and the past use into the input past use, and its past z minus 1 when the uk minus 1, uk minus 2, the past values of the inputs, plus the y's past values, so y k minus 1, k minus 2, plus the y that we want, the set point, basically the required y, into the input of the neural network to come out to give us the manipulated variable u. This is the generalized method to get the inverse model. These are inputs, this is the output, and then we compare it with the actual u that we want. Since check the error, as the error gives the required criteria or not. If not, keep on training until it gives the required criteria, then we stop at it is, and this is the inverse model they want. So this is a generalized method in general, and it is called open loop. It's inverse of that forward modeling, called open loop. We will see later why. This is a specialized method. Okay, it's slightly different. This is we have again the past inputs for mental variable, past outputs. The inputs are basically the same. Okay, the set point, the inputs are basically the same, and the output is the UK. The difference here is that this UK with the required UK is not used as the training signal, but UK goes to the system and come out with the actual output, and this output that comes from the system is compared with what we want, basically the set point value, and this is used to train the neural network. So this is called specialized method, and it basically follows exactly in the controller setup. In the controller closed loop system, as we have seen before, that this is the controller, then controller controls the model, and this is basically already in the control closed loop configuration. That's why this is called the closed loop method. The other one just now was open loop because it's not set up in the controller mode. You use it and later as in the controller. This is already set up in the controller mode. When you get this model, it directly can be used as a controller. Okay, so this is called a specialized method. From there, we can use them in different strategies in control. We have the predictive method, the indirect adaptive method, the direct inverse control method, the internal model control method. Having the forward model or the inverse model. This is where the neural network becomes a model or identifying plan or emulator, you call it, and used in the predictive method. So get the plan, is the model, goes into the optimizer will come up with the use. So this is not the neural network. It can be neural network based, it can be any other optimizer, but here mainly the neural network is used as the model itself. So this is a forward model that is used within the optimizer to get the control system. So this is in the predictive neural network predictive mode control strategy. Direct neural network as the optimizer with the model, or just as a model and not the optimizer. The other one is where the neural network acts as the emulator, basically as a plan, just like the forward model, to get the forward model plan, and also it can act as also the controller itself. Can act both as the predictive part or the inverse part become the controller itself. But here it's called the adaptive because this one is been adapted all the time. As it goes in, you adapt and keep on training the neural network to adapt and use it to check with the reference model. So it can be all the time adapted. So this one can be the neural controller itself, or some other controllers can also be used here. But whatever it is, you have to see what sort of adaptation is being used. This is indirect adaptation, adapting this one to design the controller. You can also use the neural here and adapt the neural controller itself, mainly the direct adaptive controller method. And then this is where the direct inverse control method, just like in the specialized method of training, is being trained this way. Once you get the neural, you put into this strategy, you get the direct inverse control method. The controller controlling the plant. So the inverse model of the plant is basically the control itself. If this is a perfect controller, perfect inverse model is the perfect controller for the plant. Okay, this is dynamic. Always remember, this is controls the dynamic. You have the pass inputs, pass outputs, and so on. This is the set point. So this you go straight into this as a controller itself without having a feedback. This do not have the feedback. Same thing, you have the neural network inverse model controller, you have the plant, but also you have a feed forward neural network model or approximator which feedbacks into the set point. So extra feedback, robust a bit for disturbance and so on, become robust and can cater for changes in the plant system and so on. So this is another strategy in IMC method for the neural network control. So you can see these strategies, you have to use the model as a controller itself. And we do not have to exactly follow the normal 4 elements. So of course, the neural network model control goes to the plant. Actually, we also have a valve. We have the final output control element. Okay, and also definitely we have measurements. But the measurements are all for U and for Y. So it's not like the standard measurement for Y. You also measure the Y's. We can also measure the U's. We need to measure the U's as well. So it's not like the normal 4 element strategy. Of course, you always need the control valve and the measurement, but the measurement is done in a different way. The control valve normally, the U is the one acting on the control valve. So that's why I said last time that in advanced control, the 4 element thing sometimes may be applicable, sometimes may not be applicable. Sometimes they're additional to the elements or measurement. We have many measurements we need for the strategy, depend on what type of strategy we are using. So 4 basic methods of control strategies. Basic, we have many other variants of control strategies, but these are the 4 basics that can be used using neural network: the predictive, the adaptive, the direct neural network inverse model control strategy, or the internal model control strategy. As I said, there are many variants. All of them can also be adaptive Can be an adaptive, predictive, and adaptive IMC, and so on. But these are the basic four method strategies. And once the neural network models are obtained offline, they can then be implemented in these various control strategies for the servo and regulatory control, as well as other robustness tests like with noise model. So just like the conventional, we can implement it straight into the control strategy using for set point and disturbance, as well as to study other thing, noise and from there. Just like we can study for the conventional, we can also study for the advanced different methods. But most of the time, these are advanced. They are designed offline. Means offline, they have been trained, and then once you train them, then you implement it online. But if you want to use adaptive, then we can also use adaptive online. Means once you implement it, you adapt the network model or network controller and so on. And there are so many applications in simulations, of course, hundreds of simulations, and a little bit on online so far using neural network. Basically, break up into different techniques. These are the different techniques that are being used for controlling temperature using direct inverse for semi-batch vector, using multi-layer sigmoidal for the activation function for set point and so on. So since 1995, 1993, this has been used for different processes in simulation, nothing new. Different systems in chemical process systems, and for different using neural network with different activation functions here being used for the nodes. For robustness means for set point or disturbance studies and by different people, including my work in 1996 using for partially simulated vector. So these are the different applications technique in simulation. It's already common and used and being used everywhere. This in the predictive control methods, different types of predictive is adaptation, different objective for composition, concentration, different systems. As I said again, different types of neural network and for different moments. So these are some of the summary you can find in my paper on review of neural network applications, 1999 paper. So there are huge number of work already since 1999. Lots of work using neural network for control, but this one is the inverse model control strategies. Again, IMC or direct inverse. Different objectives, different systems, different types of network, different robustness, set point, stable, regulatory, or for the servo regulatory, or sometimes just for the regulatory. Depends on what is being published in the paper by others. And adaptive control also, many types of control strategies being used for different objectives, different systems, and different types of environment. So extensive use in neural network system. You can see, you can look back and since 1999, since then there's more application. You can imagine double or triple what has been shown here. So this actual online application also quite a lot since that time. The only thing that most of them in different types of technique, the inverse model, predictive, adaptive, for different control objective, temperature, pressure level, for different systems you can see, and multi-layer sigmoidal and so on, and just like before. But this is online, but most of it is done on the lab scale and pilot plant scale. Okay, so this one is our work for partially simulated IMC on set point disturbance we did for my thesis in 1996. But again, that is a pilot plant scale. So now everything is moving towards the real world online. We've got very few at the moment, not many. There are few, but most of it is being, if it's being used real world in the industry, it's mainly neural network as a model. Like what we mentioned just now in the predictive method. Neural network is being used as a model, and inside the model predictive control. The model predictive control is being widely used in industries. But sometimes the modeling is using AI, which neural network. That is quite common. But to use neural network as a controller itself is not so common yet, because the problem is with robustness. How good is the network model to be able to robustly control in the real world if there's disturbance? So that is an issue that has to be solved. So sometimes some of it being solved, but not extensively used yet, but will be used bit by bit slowly with combination of other methods, with PI, with GMC, It's MCC. That will be a common use in the future. Of course, since AI is moving very fast in the real world application, especially under AI IR4 domain, so they will start using this thing. But it's a combination, not just neural network. We combine with a conventional or combine with neural fuzzy system, fuzzy combined with GMC, okay, combined with genetic, to make them more robust and capable, or more dependable in the real world, which cannot take for granted simulation. You can afford for it to fail and go out of control, but in the real world, it's not something that we can take chances. So they need some robustness issue to be solved and some contingency plan before it become fully applicable in the real world. But in terms of application, simulation, so many from you to choose one also for your project. As long as you can do a little bit different from what has been done by this work so far.